Hello everyone, my name is Riya Palak Bakshi. I recently graduated from the George Washington University and I will be starting a postdoc at ET at Zurich in the fall. I would like to start by thanking the organizers for giving me the opportunity to speak at the Nearly Carbon Neutral Geometric Topology Conference. So in today's talk, I will be speaking about the structure of the Kaufman brackets gain module of the connected sum of two handle bodies. And in particular, I will disprove a 22-year-old theorem about the structure of the KBSM of the connected sum of two handle bodies, and I'll provide a proof. So here's the outline of my talk. I will first speak about some preliminary notions about handles, handle slidings, connected sums, and the Temple-Lie algebra. Then I will talk about the Kaufman brackets gain module, and I'll discuss some of its properties. I'll also discuss the structure of the Kaufman brackets gain modules, and then I will talk about Kaufman brackets gain modules of handle bodies and discuss handle sliding relations in them. And then finally, I'll talk about some future work that, some future directions that my work can take. Okay, so for the rest of the talk, I will fix some notation. M3 will denote an oriented three manifold. LFR will denote the set of ambient isotopy classes of unoriented framed links, which will contain the empty link. R will always denote a commutative ring with unity, which will contain a fixed invertible element, which we denote by A. And FGB will denote an oriented genus G surface with B boundary components. Okay, so let's talk about handles, connected sums, and the Temple-Lie algebra first. So what are handles in three manifolds? So a handle of index P in a three manifold is an oriented three manifold dP times D3 minus P, which you glue to the oriented three manifold along the boundary. So a zero handle is one copy of D0 times D3, which you glue to M3 along the boundary, which is the boundary of D0 times D3, which is simply the empty set. And so you can think of a zero handle as a three ball, which appears out of nowhere. A one handle is one copy of D1 times D2 glued to the oriented three manifold along the boundary, which is S0 times D2. So you can think of a one handle as a cylinder which is glued to M3 along the two disk boundaries. A two handle is one copy of D2 times D1, which you glue to M3 along the boundary, which is S1 times D1. So you can think of this as a plate or a cup, which you glue to M3 along the annular boundary portion. And then finally, a three handle is a three ball, which you glue to M3 along the boundary sphere. So you can think of this as capping off a hole in the three manifold. So here is an illustration of what handles would look like. So a zero handle is just a three ball that appears out of nowhere. A one handle is a cylinder, which you glue to M3 along the two disk boundary portions. And a two handle is a plate, which you glue to M3 along the annular boundary portion. Okay, so what is handle decomposition? A handle decomposition of an oriented three manifold is its decomposition into 0, 1, 2, and 3 handles, and the union of these will give you M3. And a fundamental result in Morse theory says that every closed oriented three manifold admits a handle decomposition. So what is a handle body? So a handle body is a connected compact orientable three manifold whose handle decomposition consists only of zero handles and one handles. So a handle body is a connected compact orientable three manifold, and you obtain it by attaching n copies of a one handle to a three ball. Here, n denotes the genus of the handle body. One key thing to note is that a genus N handle body is homeomorphic to the thickening of the disk with N holes. So for example, the genus 3 handle body is going to be the thickening of the disk with 3 holes. Okay. So next we will talk about connected sums. So what is the connected sum of two connected three manifolds? So what you do is that you remove the interior of a three ball from each manifold, and then you glue them together along the common boundary 2 sphere. And this operation yields what's known as the connected sum of these two manifolds, M1 and M2. An important thing to keep in mind is that the connected sum of a genus N handle body and a genus M handle body is homeomorphic to the genus N plus M handle body with a two handle attached along some simple closed curve gamma. And since we know that handle bodies are thickenings of planar surfaces, this tells us that Hn connected some Hm is going to be homeomorphic to the thickening of the disk with n plus m holes with a two handle attached along some curve gamma. So let's see an illustration of this to see what's happening. So consider H2 connected some H1. This is H3, so the genus 3 handle body with a two handle attached as follows. So what you do is that you take the disk which separates H2 from H1, and then you take the boundary of the disk, which is gamma, and then you glue the two handle along this gamma. And this gives rise to H2 connected some H1. Okay, so now that we have discussed two handle addition, we are ready to talk about two handle slidings, which is also the Kirby 2 move. So how is this defined? Well, you have a component of the link and you have the disk and its boundary along which you glue the two handle. So two handle sliding will simply take this curve and slide it across this, and so that you get this diagram on the right. So for example, you have these black curves which intersect the disk along whose boundary you attach the two handle. And then by two handle sliding, you can remove this red component and have it unknotted like this. So this is one example of a two handle sliding. All right. So the last ingredient that we need to understand the KBSM of the connected sum of handle bodies is the Temperley-Lieb algebra. So the Temperley-Lieb algebra, which we denote by TL and D, D over here denotes this polynomial. It is an R algebra which is generated by n elements, the identity element and EIs, which satisfy certain relations. So the first one is that EI square is DEI when I is in between 1 and n minus 1 and including both of these. The second is that EI, EJ, EI is EI whenever I and j differ by 1. And the last one is that EI and EJ commute when I and j differ by a number greater than 1. So by a result due to Kaufman, diagrammatically, we can think of elements of the Temperley-Lieb algebra as rectangles with endpoints on the left edge, endpoints on the right edge, and then you have non-intersecting curves that connect these endpoints. So the identity element, IDN, has endpoints on the left edge of the rectangle, endpoints on the right edge, and then you have straight curves which connect the corresponding points on the left with points on the right. And EIs will have a cap which connects the I and I plus 1th point on the left edge, and there will also be a cap on the corresponding 2 points on the right edge. So we can multiply two elements of the Temperley-Lieb algebra as follows. So what we'll do is that we'll take the first element and we will glue the right edge of this rectangle with the left edge of the second element, and then we'll see diagrammatically what we get. So for example, if we consider TL3D, so that means that the rectangle will have 3 points on the left edge and 3 points on the right edge. And say we take E2 and multiply it with itself. So we glue the right edge of the first copy of E2 with the left edge of the second copy of E2. And then we see what we get diagrammatically. And we get this diagram. And for us, the trivial circle is denoted by D. So we get D times E2. So we get that E2 square is DE2. And this is in fact the first relation which was stated for the Temperley-Lieb algebra on the previous slide. Okay. So now we're ready to discuss skein modules, and in particular the Kaufman bracket skein module. So what are skein modules? They are essentially three manifold invariants. They are algebraic objects that you associate to a three manifold, and they say something about the three manifold based on the kind of knot and link theory that it admits. They were introduced by Joseph Chititsky in 1987, and there are many different skein modules. The reason for this is that you can take the knots and links in the three manifold to be oriented or unoriented, framed or unframed, or up to homotopy or up to isotopy. But what all of these different skein modules have in common is that they generalize the skein theory of the various polynomial link invariants in S3 like the Kaufman bracket polynomial, Jones polynomial, Home-Fly-Petty polynomial, Kaufman two-variable polynomial. So they generalize the skein theory of all of these various polynomial link invariants in S3 to arbitrary three manifolds. Now, since we are moving away from S3 to an arbitrary three manifold, we also need to move away from the usual knot and link projections and diagrams that are used to define polynomial link invariants in S3. So how do we do this? We do this by considering links which are identical outside of a three ball, but inside the three ball, they appear as various prescribed tangles. So this three ball is in the manifold that you're working with. And for us to be able to distinguish one link from another, inside the three ball, it is essential for us to work with oriented three manifolds. So now we're ready to define the Kaufman bracket skein module, which is the most extensively studied skein module of all. So how do we define this skein module? Well, you consider formal linear combinations of ambient isotopy classes of unoriented framed links in the oriented three manifold that you're working with. The ring over here is R, which is a commutative ring with unity with an invertible element A. And what you do is that you mod out by the submodule, which is generated by the following two relations. So the first one is the Kaufman bracket skein relation, which is L plus minus A, L naught minus A inverse L infinity. And the second one is the trivial component relation. And once you mod out by the submodule, which is generated by these two relations, what you get is the Kaufman bracket skein module, which we denote by S2 comma infinity. So 2 denotes the two horizontal diagrams, and infinity over here denotes one vertical diagram. And one thing to keep in mind is that we have this framing relation in the Kaufman bracket skein module, which is L1 minus A cube L. And L1 is obtained from L by twisting the framing of L by one positive full twist. And just for simplicity's sake, when we work with the ring of Laurent polynomials, we'll denote the Kaufman bracket skein module by a simpler notation. Okay, so this is an example of an element of the Kaufman bracket skein module of the thickened annulus or solid torus. So we have this link. We can resolve this crossing using the Kaufman bracket skein relation, and then using the trivial component relation. And after solving, we get this element in the KBSM, which is ax squared plus negative a minus a to the minus 3 times the empty link. And x over here denotes the homotopically non-trivial curve on the annulus. So this is one example of an element in the Kaufman bracket skein module of the solid torus. So some properties of Kaufman bracket skein modules are now in order. These are due to Josip Shititsky from the year 1987. So the first one says that an orientation preserving embedding of three manifolds yields a homomorphism of their KBSMs. The second one says that if you obtain one manifold from the other by adding a three handle to it, then the associated embedding yields an isomorphism of the KBSMs. And the third states that if you obtain one manifold from the other by adding a two handle along some simple closed curve gamma on the boundary, then the associated embedding yields an epimorphism of the KBSMs. So an orientation preserving embedding yields a homomorphism. Three-handle addition yields an isomorphism, and two-handle addition yields an epimorphism of KBSMs. And moreover, the kernel of this epimorphism is going to be generated by all those relations that are yielded by the two-handle slidings that I discussed earlier on. Okay. So this theorem, due to Joseph, is essential, especially for this talk, because handlebodies are thickenings of planar surfaces. So this theorem states that the Kaufman bracket skein module of an oriented surface times the interval is a free module, which is generated by the empty link and links in F, which have no trivial components. And another theorem to keep in mind is regarding the connected sums of compact oriented three manifolds. And this is due to Josef Shititsky from the year 2000. He says that if you work over the field of rational functions, then the Kaufman bracket skein module of the connected sum of compact oriented three manifolds is simply the tensor product of the individual Kaufman bracket skein modules. And one important thing to note is that this theorem does not hold when we work with the ring of Laurent polynomials, and this will be brought up later on in the talk. Okay, so the structure of KBSMs has been historically elusive, and there are few computed examples. And moreover, all the computations that have been done have been carried over various rings. So over the ring of Laurent polynomials, computations have been done for length spaces, S1 times S2, the Whitehead manifold, pair of pans times S1, certain classes of prism manifolds, exteriors of twist knots, and so on. Over the ring of Laurent polynomials localized by inverting all cyclotomic polynomials, the result is known for the quaternionic manifold. And over the field of rational functions, the KBSM has been computed for the 3 torus, for FGB times S1, and for certain infinite families of hyperbolic 3 manifolds. So, sometime in the year 2014 or 2015, Edward Witten, who is a theoretical physicist and a Fields medalist, he conjectured um, that over the field of rational functions, the Coffin-Bragg-Skene module of closed-oriented 3 manifolds is always finite dimensional. And in fact, this was proven in the year 2019 by Gunningham, Jordan, and Safronov, and they resolved this conjecture in the affirmative. And so the KBSM for any closed-oriented 3 manifold over the field of rational functions is always finite dimensional. However, this result doesn't hold for the ring of Laurent polynomials. So the point I'm trying to make is that much more is known about the structure of the KBSM of 3 manifolds over the field of rational functions than is known over the ring of Laurent polynomials. So to understand the structure of the KBSMs over the ring of Laurent polynomials is the next step. And to this end, Julien Marchais, who's a French mathematician, he conjectured that the Coffin-Bragg-Skene module of closed compact oriented 3 manifolds can be written as the direct sum of free modules and torsion modules. Now, all of the examples listed on the previous slide satisfy this conjecture. However, I showed last year that this conjecture is not true and that the Coffin-Bragg-Skene module of the connected sum of 2 copies of the real projective space is a counterexample. And this is in fact based on work by Maciek Myszkowski from the year 2011, from which it follows that the Skene module does not split as a sum of cyclic modules. So all of the examples listed before, they satisfy Marchais' conjecture. However, the moment we start talking about connected sums of 3 manifolds, we have this outlier here. So if we want to understand the structure of the KBSM of 3 manifolds over the ring of Laurent polynomials, the next step would be to understand what the structure would be for connected sums of 3 manifolds. And the first step to doing that would be to understand the KBSM of the connected sum of handlebodies. So this brings us to a theorem of Josip Przytycki from the year 2000. This was published as well. The theorem states that the Coffin-Bragg-Skene module of Hn connected sum Hm is exactly equal to the Coffin-Bragg-Skene module of the genus n plus m handlebody, modded out by the submodule, which is generated by expressions of this form. Over here, Zk denotes elements of the basis of the Coffin-Bragg-Skene module of the thickening of the disk with n plus m holes. And Zk is composed of links without contractible components and which have geometric intersection number k with the disk that separates Hn and Hm. Now, Uzk in this expression is just a modification of Zk as shown, and we get this expression from the 2 handle slidings illustrated over here. So this is a theorem which was published by Joseph. However, I recently showed that this theorem is not true. And the counterexample is in fact given by Hn connected sum Hm, where n plus m is greater than or equal to 3. And in fact, I showed that the submodule, which is mentioned on the previous slide in the theorem, it should be replaced by a strictly bigger submodule to obtain the equality stated in the theorem. So what we actually showed was that the natural epimorphism due to the embedding of H3 into H2 connected some H1 is not an isomorphism. And then in general, the natural epimorphism of Coffin bracket Kane modules due to the embedding of Hn plus m into Hn connected some m is not an isomorphism when n plus m is greater than equal to 3. So we're going to prove this theorem now. Excuse me. So this brings us to handle sliding relations in handle bodies. So let's go back to the figure that we had for H2 connected sum H1. And we see that it's homomorphic to H3 with a two handle attached along gamma. So what we will do is that we will project this onto the disk with 3 holes, F04, and we'll keep track of the fact that we have a two handle attached by drawing this red line segment, which denotes gamma. And this separates A1, A2, the two boundary components, from A3. Okay, so what we can now do is that we can work with link diagrams on this surface. So we need a nice way to represent the two handle slidings on this surface. So this is where temporally elements come into play. So what we do is that on our planar surface, in the neighborhood of gamma, we draw a temporally box. And on the outside of this temporally box, we have relative multicurve, which we denote by kappa. And we glue this kappa to the elements of the temporally box. And this gives rise to every possible multicurve on the surface that you're working with. So over here, for example, we have kappa union identity 4, because the element here is identity 4 in TL4D. And over here, we have kappa union E2, E3. E2, E3 is the element in this temporally box. So the reason why we do this is because now we can write all of our two handle sliding relations simply and only in terms of temporally elements. So it makes our calculations way easier. And the only thing that we need to do is that right at the end of our calculations, we need to embed our relations into the surface and the curve system that we're working with to see what we get in the Coffin brackets K module. Okay, so now that we have found a way to describe the two handle slidings, let's see what ZK is. So ZK is simply kappa union identity K. So if I go back, this is Z4 in F05 because you have kappa union identity 4. All right. So now that we know what ZK is, let's consider some handle slidings of ZK along the simple closed curve gamma. So one possible handle sliding is positive two handle sliding on the upper arc, which we denote by phi t. And this gives us a raised to 6 times uidk, which denotes this diagram. We could do positive two handle sliding on the lower arc, which we denote by phi l. And this gives us a raised to 6 times widk. We could also do negative two handle sliding on the lower arc. And this gives us we denote this by phi bar L, and this gives us a raised to negative 6 times W bar IDK, which is simply a mirror image of W IDK. So these are three of the many possible handle slidings that you could do of ZK along gamma. All right, so now we claim that the curve system illustrated here in F04 leads to the counterexample. And we know that K over here is 4. Okay, so now what will follow is a series of algebraic calculations. So from the previous slide, we can calculate WID3 and WID4. And we know that if we perform positive two handle sliding on the lower arc, phi LID4 is exactly the same as a raised to 6 WID4. So we get this equation. And we know that because of handle sliding, we have phi LID4 is exactly equivalent to ID4. We get this relation. And if we like to perform two handle sliding on the upper string, phi t, due to symmetry of the Templey-Lieb algebra, the roles of E1 and E3 are exchanged. So we get this relation. And we notice that all these relations are simply written in terms of the Templey-Lieb elements. Now what we'll do is that we'll subtract both these equations to get this relation. And then we will carefully take into account the strings which intersect the disk D, and we'll get some extra relations from them, which when we combine with this relation gives us this relation finally, and there's no way to simplify this. So now what we do is that we embed these temporally leap elements in this last relation into the curve system that we were working with. So for example, E1, E2, when you embed into the curve system, gives us A1, A3 and brackets A2, A3. This brackets A2, A3 just simply denotes a curve which separates the boundary components A2 and A3 from the remaining boundary components. Okay, so after we embed them into this curve system, what we get is that in the Coffin-Bragg gain module of H2 connected sum H1, we have this relation. But the right-hand side over here is not contained in the submodule, which was defined in the theorem. So we get that the submodule in the theorem needs to be replaced by a strictly bigger submodule for there to be equality. And since handle bodies of smaller genus can always be embedded in handle bodies of higher genus, so this gives us the counterexample for Hn connected sum Hm, where n plus m is greater than equal to 3. So we have found the counterexample for n plus m greater than equal to 3, but what about H1 connected sum H1? What is the structure of the KBSM of H1 connected sum H1? Does the submodule need to be bigger in that case as well? Well, we conjecture that that is indeed not the case. In fact, we conjecture that the natural epimorphism of the Coffin-Bragg gain modules due to the embedding of H2 into H1 connected sum H1 is indeed an isomorphism. And in fact, this has been proven by Thangle and Josef Prititsky joined with me, and is going to be up on arXiv soon in the summer. So the goal that we need to keep in mind is that we're trying to understand the structure of the KBSM of connected sums of three manifolds. So the next step after this would be to generalize this result to the connected sums of all length spaces and move forward from there. This brings me to the end of the talk. Thank you so much for listening. You may find the paper up on arXiv. It's also published in Manuscripta Mathematica. And if you would like to discuss any of my work, any of my papers, or this talk with me, please feel free to contact me at riyapalakbakshi@gmail.com. Thank you so much for listening. I hope you have a wonderful day. Bye-bye.